Hello everyone. In this video, let's try to solve some another regression problem. So the problem that we are trying to solve is prediction of ice cream sales based on temperature as the input feature. So if you observe the data, we are having two columns over here. One is the temperature and the other one is the ice cream sales. And it is in units, whereas it is in the degrees centigrade. So these are all different temperatures and the corresponding ice cream sales information. Now let's try to see how we are building the model for this. So for regression problems, we know that we can use linear regression. So first we are importing all the required libraries like NumPy, Pandas, and Matplotlib. After that, we are reading this ice cream selling data.csv, which I am keeping in the same folder where this particular notebook is. And then I'm trying to load directly. And if you use df.head, it will be giving us the top five rows. So these are the top five rows in my particular data set. So this top five will be getting over here. Okay. And after that, like we'll be keeping my input column that is temperature. So first time this means that I'm selecting all the rows, whereas this means that I'm only selecting first column. Okay. That I'm selecting and keeping it in X, whereas my output column I wanted it in Y. So that's why here I'm selecting all the rows, whereas in columns I only selecting the first column. So first column is our ice cream sales column, which is our output. And if I observe the X dot shape, there are total 49 points in our whole data set. And if you wanted to observe those data points, we can print this particular X, and X contains only the inputs, right? That is my temperature values. So these are all the temperature values that I'm having. And similarly, the corresponding Y's are in this particular NumPy array. Okay. Now, before going on to building the model, what we need to do, we need to split the data. So for that, we can use this train test split. So here I'm mentioning test size to be 0.25, which means that 25% of the points will be going into the testing data set, whereas the remaining 75 will be going into the um, training data set. Okay. After division, in my training data set, I have 36 points, whereas in testing data set, I'm having 13 points. Similarly, in white train and white test, corresponding outputs to these we'll be having. And then we can simply build some linear regression model using linear regression function, which got imported from that sklearn.linear model. And then we can fit our training data. And after fitting, we can get the coefficient and intercept. That is, if like the hypothesis for linear regression is y equal to mx plus c, right? So in that m and c values, you can think of these values. So this is the intercept. That means the c value, whereas this is the m value. Okay. So these values we got after training. Okay. So, and we have discussed regarding the score as well. And what score we'll be using? We'll be using something called as R2 score. So if you observe on training data, the score that we are getting is very less, that is 0.02. And on testing data, it is even minus. Okay. By seeing this, we can understand that the model that we are getting is underfitting. So the score on the training data itself is very low, right? So by seeing this, we can clearly understand that we're underfitting to the model that we are having. Okay. And let's try to see how it is predicting. So for these inputs, these are the prediction values, and let's try to see visually. So here, these are all my training data points. For these kind of training data points, I'm trying to fit some straight line like this. So if we are able to fit some U-shaped curve, then it will be better, right? Instead of this straight line. As we are trying to fit only straight line, that's why the score that we are getting is very less. Okay. And similarly on testing data is also similar to that. And here also we are trying to like find out ice cream sales with the help of same line. So that's why we are not able to get proper score for that. That means we are underfitting. So whenever we are underfitting, what we can do? So here if we see, let's say we are having some equation like y equal to mx plus c, right? Or you can write it as y equal to theta naught plus theta 1x. And the data that we are seeing over here is something like this, like some U-shaped curve like this. But if we see, this is equation of a straight line. So with the change of these two values, that is theta naught and theta 1, we can only obtain lines. So we can obtain any kind of line. With these lines, the maximum R2 score that we can get will be very low, because it will like if you're drawing any line, it will not be near to most of the points. Let's say we are trying to draw this particular line. So this is the line that we are trying to draw. The like the amount of loss that is made on all these points is very huge, right? So that's why the score will be very less. Okay. So that is the problem with this. So in such times, how to proceed? So in such times, what we can do is we can increase the complexity of the model, and we can increase that with the help of some technique called as feature engineering. So what is the technique? The technique is feature engineering. So till now we are able to draw only straight lines, right? Now let's do some feature engineering and obtain new features. So feature engineering is like, let's say we are having length, and first suppose we are having breadth. Let's say these are my two features, and these two features individually are not helping me in any way. Then what can I do? I can use some other feature which is combination of these two, like length into breadth. So which is area in some cases, right? So we can use this specific length into breadth and maybe find out the answer, right? So that means we are trying to change the inputs in some other way which will be useful for us. So that is nothing but feature engineering. Similarly, here if you observe, we are having only one input, that is x, right? So here the only input that we are having is x, and we are not able to find proper solution for this. So what we can do, we can use higher degree features. Like let's say we are trying to obtain degree 2 features, then my new feature will be x square. So I'm having x, and along with x, I'll be having x square as well. And what will be the corresponding hypothesis? So my hypothesis is this one previously. As I'm having extra feature, my current hypothesis will look like this. Okay, it is theta naught plus theta 1x plus theta 2 x squared. Now we are having this extra term, right? So this whole thing will be my hypothesis. And with this, I will be able to fit something like these U-shaped curves. And why is that? So if you guys know, there's a graph of x square, it will look like this. Let's say this is x and this is x square. So for input 0, it will be 0. For input 1, it will be 1. For input 2, it will be 4. For input 3, it will be 9, right? Because like we are trying to find square. So for 1, let's say this is 1. So this will also be 1. This is 2. Then this will be 4. And for 3, it will be 9. Okay, here we'll have 9. Like that, if we go towards minus, then we'll have 1, 4, and 9. So like this, we'll be getting some U-shaped curve if we are using x square, right? So on changing these values, we can get like different types of U-shaped curves, and also we can get straight lines as well. How we will be getting straight lines? Like let's say if this is made to 0, then with this we can obtain all the straight lines, right? So with the help of this whole equation, we can obtain different types of U-shaped curves, and also we can obtain all kinds of straight lines. So like this, we can make our model more complex and we can use it. And even on using these two features, let's say we are not able to fit properly. That means we are underfitting. Then what we can do? We can increase to even higher degree. That is now we'll move on to degree 3. Okay. So like that, if you're moving on to degree 3, I'll be having features like x, x square, and x cube. My corresponding hypothesis will look like this. That is theta naught plus theta 1x plus theta 2 square plus theta 3x cube. Like that, I can add as many features as I wanted, and I can make my hypothesis more and more complex so that it can fit more number of points. Okay, so this is what that we can do with the help of higher degree features. And this technique we call it as polynomial regression. Okay, so this we call it as polynomial regression. Till now we have discussed on linear regression, in which only degree 1 features will be there, whereas in case of polynomial regression, we'll be having higher degree features. And till now we have only seen uh, like examples with one feature, right? But it can happen that there can be multiple features like this x1, x2, x3, so on. So my hypothesis for such kind of points, it will look like this: theta 1 plus theta 1 x1, theta naught plus theta 1 x1, theta 2 x2, so on, theta 3 x3, and so on. Like as many features we have, those many thetas we will be having. And what are all these thetas? These will be my parameters. and these will be adjusted with the help of the optimizer. And what is our optimizer? Our optimizer is some gradient descent algorithm. Okay? And this we call it as multi-regression. Okay. So multi-regression is like having multiple number of features. So this is multi-regression, and having higher degree features, it will come under polynomial regression. So now let's try to quickly understand the combination of these multi and polynomial regression. Let's say we are trying to solve some problem in which there are two features x1 and x2. Okay. So for these two features x1 and x2, how will my hypothesis will look like? That is y equal to theta naught plus theta 1 x1 plus theta 2 x2. But let's say like this is my hypothesis and I have some loss function. What will be my loss function in case of linear regression? If you guys remember, it will be MSE, that is mean squared error. Okay. And after calculating the loss, we'll use optimizer, that is ZD. So with the help of this optimizer, we'll adjust all these theta naught, theta 1, and theta 2, right? And again, we'll be observing the loss and continuously we'll be looping till these will go to their optimal values. So this is what happening internally. And after these values have gone to their optimal values, then like let's say even then we are not able to get some good R2 score. So we are not getting good R2 score even after going to their like optimal values that is given by the optimizer, or like this algorithm is getting stopped due to some reason and we are not able to reach the exact optimal. Even then R2 score will be less, right? So what does that mean in that case? That means that we are underfitting. So in underfitting, what we can do, we can make our model more complex. And how can we make my model more complex? With the use of polynomial regression. And what is the idea of polynomial regression? The idea of polynomial regression is to add some higher degree features, right? So now let's try to add degree 2 features. So if you're having x1 and x2 as my input features, my corresponding degree 2 features will be x1 square and x2 square. Along with this, I'm also will be having x1, x2. So these are all my degree 2 features. Along with this, I'll be having x1 and x2 as well. Okay. And the corresponding hypothesis will be theta naught plus theta 1 x1, theta 2 x2, theta 3 x1 square, theta 4 x2 square, theta 5 x1, x2. Like that, when I'm having multiple features, I can do polynomial regression. Okay, so I hope this is clear for everyone. And if you guys have any kind of doubts, you can comment down in the comment section. Now let's go to code. So here, if you observe, we are not able to fit good with the help of this linear regression. So we'll be moving on to polynomial regression. So in order to move on to polynomial regression, what we can do, we can simply use these poly features from sklearn.tree processing, and we can mention whatever degree that we wanted to increase or make our model complex. Okay. So let's say if I wanted to use degree 3 features, till degree 3 features, then I can use 3 over here. But for now, let's take only 2. Okay. In general, we should not jump like this. Like directly from degree 1, we should not move on to higher degrees like 5 or 10. And why is that? Because it can happen that my model will become more complex. And if my model becomes more complex, then what will happen? Let's say I am having different points like this. It will try to fit for each and every point. If it is trying to do that, then what will happen? The training score will become very high, that is near to 1, and my testing score will be very low. Okay, and it leads to overfitting condition. And overfitting is also not good thing to happen. So that's why we'll not increase directly to very high powers. We'll try to move by either like from 1, we'll try to move to 2, or we'll try to move to 3 at max. Okay. And even if these two are not working, then we can try for higher degree powers. So let's see, here we are using degree 2, and then we are using this particular polynomial features in order to generate higher degree features. So in order to generate, how we are doing, we can simply use poly.fit transform on xtrain and xtest. Okay, so here if you observe, basically here 0 degree power is also getting included, that is uh, x bar 0, x bar 1, and x bar 2. And what is in this particular x, in x, if you guys remembered, we are having this temperature column. So all these temperature values will be taken So that is x bar 0 is always 1. That's why here it is 1. And this is x bar 1 and this is x bar 2. Okay. And this is for testing data. This is like x bar 0, x bar 1 and x bar 2. And now we'll simply use this linear regression. But now we have multiple features, that is x bar 0, x bar 1 and x bar 2. So that's why I'll be having the intercept, and also I'll be having, as there are three features, I'll be having three corresponding parameters. Okay. So this you can think of it as theta 1, theta 2, and theta 3. And here if we observe it is 0. That is because, like, here if we observe, let me redraw this. It will be like y equal to theta naught plus theta 1 x bar 0, theta 2 x bar 1, and theta 3 x bar 2. Okay. So what is x bar 0? It will be always 1, right? So that means it is like theta naught plus theta 1 and theta 2 x bar 1 and theta 3 x bar 2. So instead of adjusting two parameters, what the model is doing, the model is internally optimizing it, and it is adjusting this to be 0, and it is only trying to adjust this theta naught. Like that model is internally doing some kind of optimization by observing this data. Okay. So that's why it is 0, and these are the corresponding theta 2 and theta 3 values. And now if you observe the training score, it is 93. And what is our testing score? It is 0.92. So that means it is really good, right? And these are my predictions. And now if you observe the graph, my graph is looking like this. To these points, we are trying to fit some U-shaped curve like this. And similarly, for these testing points, we are trying to fit some U-shaped curve like this. So like this, we can use polynomial regression and we can solve for some of the complex problems, okay, or some of the problems which are not linear, for which the data is not linear. Okay, so this is the idea of polynomial regression, and if you have any kind of doubt, please comment down in the comment section. And thank you everyone. Bye bye.